Good morning or good afternoon. We are going to go ahead and start our unit on limits. So this is our first official unit in calculus. We're going to talk about the introduction to limits today, the idea of what it is and how we look at them graphically. You have been given a gold sheet. This is what's going to tell you when your homework is each day, when your quizzes and tests will be. I realize that some things may need to be adjusted as we go, but please keep this gold sheet very close to you so you can look at it each day for your book homework. You'll notice tonight you have an assignment. There are some book problems that are bolded and underlined. Those are the ones that I need you to do. The ones that are not bolded and underlined, those are suggested if you need extra practice. Okay? In my opinion, I think you should do all of them, but I also understand that sometimes we have to be careful with our time. Okay? I also have the gold sheet uploaded at the beginning of Unit 1 in Google Classroom, so that is something that you can look for. Okay? All right, so a limit is the behavior of a function as x approaches some value. Okay, so the key word here is that word approaches. So we're looking at what our y value is doing as x approaches some value. So we're getting closer and closer and closer and closer to a value, but not necessarily getting all the way there. Okay, so if you look at this table of values, you can see that as we come from the left side with our x's, and then from the right side with our x's, our x values are getting closer and closer to 1. So we would write the limit as x approaches 1 of our function f of x. Okay, now let's look at these y values. If we look at what our function is doing, as we get closer and closer to x is 1, what's happening to our y values? Okay, well, it looks like our y values are getting closer and closer to 3. Now, this table of values, this is not how you are going to evaluate limits, okay? This is for us to start getting an idea of what it means, all right? So let's go ahead and look at what this function is, okay? So here is our function x cubed minus 1 over x minus 1, okay? And we just determined from our table of values that the limit as x approaches 1 of f of x equals 3, okay? Now let's look at this graphically, okay, because this is going to be important, okay? So here is our graph. You'll notice that at the coordinate 1, 3, our graph has a hole, okay? Remember, when we can cancel out factors from our numerator and denominator, we are left with a hole in our graph, okay? Whoops. What I want you to think about, okay, if we were to follow the function, so here is x is 1. As we come from the right side along the curve, and as we come from the left side along the curve, we are getting closer and closer to that hole. Now I know nothing is there, but our y values are getting closer and closer to that hole, where the hole is at 3. What I want you to imagine is if there was a car driving on both sides of our function, and what's going to happen is, where are these two cars going to crash into each other as we get closer and closer to whatever x value that is? Okay, so I'm going to keep this graph on here, and let's say I want to know the limit as x approaches 0 of f of x, okay? Well, if I look at our graph, here's x is 0. And if we follow the curve from the right side, and if we follow the curve from the left side, it looks like our y values are getting closer and closer and closer to 1. Okay, so that would be our limit. Whether there is a hole there or whether there is a coordinate there, that's what's going to help us determine what that limit is. Okay. All right, so this is the last time we're going to use a table. Okay, this is the last time we are going to use a table. Okay, so let's go ahead and this is what I'm going to have you do. If you have a pink rag under your chair, I want you to plug in these two x values. Okay, and how about we do this? If you have a pink rag under your chair, plug in these two values to our function up here. Okay, so this is the function you're plugging into here. All right. If you have a green rag under your chair, please plug in these two. If you have a blue rag, please plug in these two. And if you have a yellow rag, please plug in these two. Okay. Okay, so here's are the values that you should have gotten when you plugged in your values. Okay. Now, as we look at the limit, as x approaches 2 of our function, so as our x values get closer and closer to 2, then it looks like our y values get closer and closer to 1. Okay? Now, like I said, I don't want you using these charts to help you figure out. Okay, that's a lot of work, a lot of tedious work that I don't think that we need to be doing. So let's go ahead and think about this graphically. So what I want to remind you of is that when we have a rational function, it is always a good idea to simplify if we can. So our numerator, we can go ahead and write that as x minus 2 times x minus 1. And the x minus 2's cancel. So what's happening is we have the graph of x minus 1 but we have a hole wherever we canceled out those factors. Okay, so here's our graph. Okay, so if we look at our graph, okay, and we imagine, if you want to, our car is driving along here. Okay, as we approach x equals 2, they would run into each other where this hole is, which is at y equals 1, and that is what our limit would be. Okay, essentially we're looking for that y value of the coordinate that we are trying to approach. Okay. Now, here is an interesting graph. We have a graph with a hole, just like we've seen. But look here, there is a coordinate here at 2, 0. Now, if we look at the limit as x approaches 2 of this function, remember, we need to think about where our cars are driving, and our cars are always going to be driving along the curve. So here's where our cars would be driving. If they follow the curve, as they get closer and closer to x is 2, they're going to crash into each other here at this coordinate right here. So the limit as x approaches 2 of f of x would be 1. Now, if I asked you for f of 2, well then that answer would be 0 because that's where our coordinate is. Our coordinate has a y value of 0, but our function has a limit of 1 as we approach x is 2. Okay, so the limit is describing the behavior of the function, whereas the function value is just where that actual coordinate would be. Okay. Now, you are going to have times where a limit is not going to exist. Okay, so there's 3 different scenarios we need to be aware of here. Okay, the first one is this. If we have differing behavior from the right and the left. If we have differing behavior from the right and the left. Okay, so just pause your pencils for a moment. Okay, I want you to look at this graph and then I'm going to have you write it down, okay? So if I'm asking you for the limit as x approaches 0. Well, here is x approaches 0, right? Well, if we drive our car from the right side and if we drive our car from the left side, notice how as we get close to 0, those 2 cars are not going to crash into each other, okay? From the left and from the right, they are approaching 2 different values. From the right side, we are approaching positive 1. From the left side, we are approaching negative 1. Okay, now go ahead and write down that this is the limit. Okay, and then go ahead and write down that when we evaluate it, the limit does not exist. So the way that we write that is right here. DNE, does not exist. That's our shorthand, okay? The limit does not exist. And if I asked you why the limit does not exist, then you can tell me that the function is approaching a different value from the right than from the left. Now, I also want you to go ahead and draw this graph. This is going to be a graph that I am going to expect you to remember. Okay, y equals the absolute value of x over x. We have an open circle and a line to the right at 1, and an open circle and a line to the left at negative 1. Okay, I'll also expect you to be able to do some transformations with this graph. Okay, for example, if I asked you something about the graph the absolute value of x minus 2 over x minus 2, we know that that looks the same except we are shifted to the right 2. So this is what our graph would look like. Okay? All right. The second way a limit could fail to exist is when we have what's called unbounded behavior. Okay, so here's way number 2, unbounded behavior. And the graph that we're going to look at is the graph of 1 over x squared. Okay. Okay. Now, if I asked you for the limit as x approaches 1 of 1 over x squared, okay, we actually have a coordinate that we'd be approaching, okay? That limit would be 1. However, when I ask you for the limit as x approaches 0, that's a different story. Notice how, so here's x is 0. From the right side, here is where our car would be, okay? From the left side, here's where our car would be. We're just going to keep going up towards infinity, okay? And infinity is not a value, so we say that the limit does not exist. If we are approaching infinity or if we are approaching negative infinity, we say that we have unbounded behavior and the limit does not exist. Now, I will mention that here in a couple more lessons, we will be able to describe that behavior that does not exist, but we're not there yet. We're just saying that the limit does not exist. Okay. And then the third and final way a limit fails to exist, and this is the one that we see least often, okay, is what we call oscillating behavior. So we know that like a normal sine function bounces between -1 and 1, and it does so evenly, okay? Look at this crazy graph right here. This is the graph of sine over 1 of x, and what we have is the limit as x approaches 0 of sine over 1 of x. And as we try to get closer to x is 0, we have no idea what's going on inside, okay? We have no idea, between here and here, what is happening because it's oscillating so quickly. And so we have no way to determine what our limit is, okay? Like I said, this is one that's going to be the least often seen, but it is our third case, okay? So the limit as x approaches 0 of sine of 1 over x does not exist. And if I asked you to tell me why, you would tell me because of the oscillating behavior. Okay. What I'm going to ask that you do, and it does not have to be pretty, but just quickly draw this graph in your notes so that when you go back and look at your notes and you see the examples that we've done, you can understand where your numbers came from. Okay, so let's look at these. First, the limit as x approaches 3 of f of x. So here, this is our function, f of x. Here is x is 3. Well, if I look at the coordinate, and I know that there's not a coordinate drawn on there, right? But there's graph, right? So I know that our y coordinate is right here. Okay, there is a coordinate there. It's just not like big like the others, okay? So there is a coordinate right here. So if we drive our car from the left, if we drive our car from the right, it looks like that function value would be at about 1.5. You know, it's kind of hard to say exactly, but we can estimate right there that it would be 1.5. Okay. Now, let's look at the limit as x approaches 1 of f of x. Okay. Well, here's x is 1. From the right side, we would be approaching 1, but from the left side, we would be approaching like 3.5. Since those are different, since we are approaching two different values from the right side than the left side, then we're going to have to say that our limit does not exist. Okay. However, our function value at 1, f of 1, we can determine. When x is 1, we have a coordinate right here, and its y value is 2. Okay. And then finally, we have the limit as x approaches 4 of f of x. Well, here is x is 4. If we come from the right side and the left side and we drive our cars would crash into each other, and the y coordinate that they'd be crashing at would be y is 2. That is where that hole is that we're approaching. Okay. Something that I want to give you the analogy of, a limit is kind of like an annoying little brother or annoying little sister, or maybe a cousin or a neighbor, or maybe a pesky friend. You know that game where somebody comes up to you and says, I'm not touching you, I'm not touching you, I'm not touching you, but gets their finger really, really close to you just to be annoying, okay? That's kind of what we're doing. We're getting annoyingly close to whatever coordinate it is without touching it and saying, okay, that's the y value. Okay, so here is our last example. I want you to look at this graph and I want you to determine all of the x values in which the limit fails to exist. So you don't necessarily need to draw this right now. What I want you to do is just take a moment and determine the x values in which our limit fails to exist. Okay. Turn to your neighbor real quick and discuss the values that you talked about and how you know. Okay. So the first place that we have a limit that fails to exist is at -2. You could describe this as either unbounded behavior or approaching different from the right and left. Okay. The second place is at x equals 0 because the right and the left are approaching different values. Okay. And then the last one is 4. X equals 4, we have unbounded behavior, and so the limit is going to fail to exist. Okay, we do indeed have a limit as x approaches 2. From the right side and the left side, we are approaching that hole, and so we could describe that limit. Okay, so if you're watching this in class, then what I'd like you to do is get organized for doing your homework. You all have access to the book in your Google Classroom. Under Unit 1, the first thing, and I haven't done that yet, so I'm doing that right after I make this video. So I am going to go to Google Classroom to show you something, but your textbook's not going to be there quite yet. So in Google Classroom, if you haven't uploaded your homework, please take the time to do that. Okay, so when you go there today, you're going to see Unit 1, and in Unit 1, there's going to be a PDF of our Chapter 1. Please use that for your book if you don't have it with you. The next thing I want to show you is Calc Chat. Okay, Calc Chat is a way for you to check your answers from the back of the book when you don't have the back of the book. So if you just click on the link in this Calc Chat post, it'll open you up to the book. Okay, so you can select Chapter 1, we're in Section 2, Exercise 5, and it will show you not only the answer but the solution as well. Okay, so if you don't have your book, you can use the PDF version in Google Classroom. And to check your answers, you can either use the back of the book or you can use Calc Chat. Calc Chat is a good place to go to also if you need some help kind of guiding your first steps and you want to look at how the solutions have done it. If I give you an even problem, even though those aren't in the back of the book or in Calc Chat, you could look at an odd problem similar to it to go ahead from there. Okay?